Hi there. Welcome. Today I'm going to be discussing a horrible, terrible, no good, very bad circuit. Without overloading you of the details of every definition, I'm going to just explain how to solve a fairly mind-boggling circuit. So, a closed circuit connects end to end. Your wire or other form of continuity presents a very low resistivity to charge. It's spatially compact. And with those assumptions, the wire in the circuit forms a good approximation to how electric circuits actually behave. We also have a voltage source, a battery, which I'm sure you're familiar with. It's measured in volts, so typical battery is about 1.5 volts. And we also have a concept of ground that you might not be familiar with, but essentially it's an object that totally dismisses charge. So if a whole bunch of electrons pile in here, it's so big that it doesn't feel it. It doesn't show up. So the voltage from the battery is effectively like floating over this ground. And this kind of hides it, but we do have a complete circuit because presumably at the other end of this and all the circuit elements, there's another ground connected. So it's ground to ground, and there's a battery in there. So in a circuit with the voltage source here, resistors can be said to drop voltage. See, if we were to walk along this direction, you'd see a different polarity at the resistor against the polarity that the battery gives you. And this is actually codified. Well, first off, it depends on the number of ohms, the amount of resistance of the resistor, which is kind of just a product of how it's built. But we can codify this statement that the voltage drops as much as it rises in what's called Kirchhoff's voltage law. I'll spell that. And Kirchhoff's voltage law says that the sum of voltages through any closed loop is zero. So we know that along any loop, any voltage we provide is going to be consumed by any circuit elements there. Okay, so in this case, we have the battery of the voltage minus the voltage across the resistor, which is measured this way. And that gives us a clear statement about how this circuit will behave. So next, you're probably well aware of something called current. So current measures how quickly the charge passes through the circuit rather than how much kind of pressure you have from voltage. And that's important to understand because in this resistor, we can predict the amount of voltage that it's going to drop and the amount of current that it's going to produce using Ohm's law. So we have Ohm in two places now, both the amount of resistance and this law that I'm about to highlight for you, that the current and the resistance of a circuit element are proportional to the voltage. So basically, you just multiply the current times the resistance, and you can get the voltage. And this can be rearranged a couple different ways, where if we only know the voltage and the current, we can figure out the resistance. If we only know the voltage and the resistance, we can figure out the current. And I think that's pretty much all the useful permutations for Ohm's law in this case. So now we've introduced a junction. So a couple things to draw your attention to. There's actually two loops in this circuit, calling back that KVL rule, and that still holds. But in this case, what this means for us is that we can seek the equivalent resistance of this. But this junction also implies another rule called Kirchhoff's current law, and that says that the sum of currents through any junction is equal to 0. So if there's one current that's shared by this that's coming out of this voltage source, then that current also has to come out of the junction, okay? So this is different from Kirchhoff's voltage law because we're not talking about loops, we're instead talking about junctions. And this also makes sense in the trivial case because let's say you choose this as your junction. You're not going to expect through this conductor for a whole bunch of charge to appear. You're not going to expect a whole bunch of electrons to come out of nowhere. So it's the same thing when you have 3 different branches. So we'll actually have 3 distinct currents here. And so if I1 is the current going in, then I2 and I3 has to come out. And we can use the distributive property in algebra to write this a little bit differently, just to show that the I2 and the I3 kind of have the same privilege level, right? They're both going to have the same sign. So we can also find equivalent resistances. So if we have 2 resistance with 2 different numbers of ohms, there's a relationship. We can solve this algebraic expression, and it will tell us an equivalent resistance. So that's useful for finding this current here. So if you only know the voltage, you only know the ladder of resistance, then you can find that incident current. This also extends for arbitrary numbers of resistors. So if we have a whole bunch of resistors at the other end, we just add them up just like that. You can follow the pattern. And then for series resistors, these are all going to have the same current incident on them, and they're all going to be dropping the same voltage. We just add. Couldn't be simpler. And now we come to this thing. How do we find the equivalent resistance of this? I won't beg that question too much, but it's kind of a mess. So you may be tempted to claim that these 3 resistors are in parallel, but that's actually not the case. And none of these can be said to be in series with one another because there's junctions between all of them. So that kind of defies the claims that we've made about equivalent resistance. So we've connected this to a power source now, as well as a ground. So through this cube of resistance, we do have a complete circuit. And we'll also say at this stage that the resistance of all the different resistors, and we'll solve it in general, but in this case, all of the resistors have the same value, the same number of ohms. So with a little bit more detail, we start to label them. And we're going to splay the cube out. This is kind of called a breadth first. So I've labeled all the resistors that connect directly to the voltage source. And then I've started to label the ones that connect to the first, and then I can label the ones that connect to the second. And that's all to the effect of having a correct topological representation. So you can verify that these two are equivalent. And that will net us a pathway to a solution for this. It's a little bit easier in this representation to demonstrate that you cannot use series parallel, because if you claim that A is parallel to B, you also have to claim that A and then DE parallel in series with it. It's all kind of interconnected. There's no good way to go about that. Another tactic that I've used is to try and pass A back through the power source to ground, but it can't slide past B and C because there's a proper junction here. So instead, I've identified these two principles that we can use. So the first one says the set of minimal paths from terminal to terminal form a linearly independent set of closed loops. So through any of these different bounces that our voltage source would do, we can extract useful information about the circuit. Linearly independent is kind of a complicated word, but it basically means we're not writing the same relationship down twice, so we don't confuse ourselves with whether or not we have all the important details about the circuit. The next one says the set of interior junctions form a linearly independent set of ideal junctions. Okay, so what that means is excluding the outer two junctions, it's kind of ignoring those. All of these interior ones bear significance about how we can analyze the circuit. Okay? So to deal with that, we first look at one volt path of the circuit. So we start here, and we know that we have a voltage V at this point relative to our zero ground. Okay, so measuring across any of these paths, we'll have a voltage of V, whatever our voltage source is providing. And then if we choose one path, and why not the top, we'll have a voltage drop between A and D, and then we'll have a voltage drop across D, and then we'll have a voltage drop across X. And that forms one path, and those all must add up to V based on our Kirchhoff's voltage law. And then the next step, I'll demonstrate one junction. So the current going into this junction must be the current going across A. And then the current across these two junctions must be equal to that, because there's no other source of current in this single specific junction. So we write that relationship down. And then realizing that since we know that A, D, and X will all have the same resistance, R, that was part of the problem setup, we can just write down that the voltage drop is going to be using Ohm's law, the current and the resistance, just the product. Okay? Now repeat for the 12 different equations present, and suddenly we have a system of equations. You've probably seen these in algebra trivially, so 2 or 3 equations, and it's not too hard to do back substitution, but this is a mess. There's actually formal process called Gaussian elimination that can systematically solve this, and that's likely what we'll end up using. So I actually have some software pulled up called Sage, provides a Jupyter notebook, and what we can do is just declare all of our currents and then declare a voltage and a resistance. And then the next step would be to produce the system of equations. So I'll just write this out once and then quickly change up all the variables. So we'll have 6 equations that kind of look like this. Sorry, I know riveting data entry here. And assuming that I successfully write down all of these relationships without making any clerical errors, so these are the applications of Kirchhoff's current law to the junctions of the circuit. And then we're going to tell our equation solver to solve for the currents effectively. Yes. When an equal sign is not an equal sign. And then there we go. So we've asked our computer to solve this system of 12 equations for these 12 different currents. And with that in place, recalling this fact that the total current and the input voltage will give us the equivalent resistance, we'll just add up the given input currents. So if I add up these 3 currents that we've found, we now have a relationship between the given resistor, which is R, any arbitrary voltage, and the input current. Okay? So now a little bit of algebra to solve for the equivalent resistance will give us V over I ABC equals 5R over 6. So we've actually shown that the equivalent resistance for any voltage and the resultant current is going to be 5/6 R. And this actually differed from the way that the book found the solution, which was another interesting method, but to essentially assume equipartition of the incoming current. So because none of these are privileged, these all have the same R value, then they must also have the same current. And then similarly at the interior stages, because none of these are privileged, they all must have the same current. So that R value implies that each of those currents are going to be I over 3. Each of these currents are going to be I over 6. You can solve this through a different method. But that's all. Thanks for watching.